Good morning to one and all. Good morning. So I have resumed the audio, video, and screen. Yeah, please kindly confirm audio, video, and screen. Please kindly confirm audio, video, and screen once. Yeah. Yes. Okay, fine. See, the next element, what we said in the yesterday class, that is a series capacitor. So it was series element as usual, we know. So it is going to modify the series impedance of the transmission line, particularly series reactance value. It is going to reduce, in fact. Okay. So it reduces the series reactance of transmission line. Series reactance of transmission line. Reduces the series reactance of transmission line. Okay, next thing. See, whenever if you have a lagging power factor load at the receiving end side, and if you add a series capacitor, lagging power factor load at the receiving end side, and if you add a series capacitor, the receiving end voltage magnitude will rise up. Okay, right. So it increases the receiving end voltage magnitude, means I will say simply mod VR, increases the receiving end side voltage magnitude mod VR for lagging loads kept at receiving end side. Kept at receiving end side. Kept at the receiving end side. Whereas if you have a leading power factor load at the receiving end side, leading power factor load, it will be decreasing the voltage magnitude. So it decreases the receiving end voltage magnitude mod VR for a leading power factor load, means leading loads kept at receiving end side. Kept at the receiving end side. Kept at receiving end side. Okay, fine. So I will explain about both statements, what we have written, or what will happen for lagging load as well as what will happen for the leading power factor load. I will explain both of these. Okay, let's move ahead. With two cases again, case one without series capacitor and case two with series capacitor. And we'll see how that receiving end voltage magnitude is going to be changed. See, case one, I am taking. So it was a source. This is a transmission line we have. And at the end, I am taking lagging load only because it's a practical load, what we can experience. Lagging load. Sending end voltage we are calling mod Vs. Receiving end voltage I am showing as VR1 without series capacitor placement. Till now, we have taken that line with only series inductive reactors. Now I am keeping that resistance also, but there is no difficulty in that. Either you take the resistance into calculations or neglect the resistance, it makes no difference. But for our convenience, I am keeping that R plus JX here. RL plus JX. Line resistance and line reactance. If resistance is not given, you can neglect. Okay, next thing. Current flow in the transmission line is I. Lagging load we said at the receiving end side. Now, let us say the power factor of this load, or you can call the receiving end power factor also now. It is cos pi r lagging. Receiving end power factor we are saying as cos pi r lagging. Just look at this diagram. We have discussed some things in short transmission line long back. I am recalling that concept what we studied in the short transmission line, right? So I'll write in short transmission line, we have taken up an expression for mod Vs minus mod Vr. Mod Vs minus mod Vr, something like magnitude of current magnitude of impedance, cos of theta minus phi. I think all of you understood this one. Are you capable to recall this equation, what I have written? Mod Vs minus mod Vr equals to mod I into mod Z cos of theta minus phi. Yes or no? Phi. Phi in the sense phi r also you can say now. Theta minus phi r. And after doing that expansion, you came to know that mod I into line resistance into cos phi r plus mod I into line reactance into sin phi r for the lagging load. For the lagging load, you will be getting it as mod I into line resistance into cos phi r plus mod I into line reactance into sin phi r for the lagging power factor load. Lagging power factor load. Okay? Yeah. See this. See this. See this expression we are going to apply for the present case. For the present case means what you should write mod Vs minus mod Vr1 now. Mod Vs minus mod Vr1 equals to mod I into RL cos phi r. It's a lagging load plus mod I into XL sin phi r. Okay, right. So I'll write now in the case one. Sending end voltage minus receiving end voltage, magnitude difference. Magnitude difference will be mod I into resistance RL into cos phi r plus mod I into XL into sin phi r. Mod I into XL into sin phi r, you can see. Like this, you will have mod Vs minus mod Vr1. Mod Vs minus mod Vr1. And it's a very well-known thing that this whole number is a positive value. So Vs minus Vr1 is a positive value for us. So definitely receiving end voltage Vr1 will be less compared to Vs in magnitude. Receiving end voltage Vr1 will be less compared to Vs in magnitude. Is that okay? Is that okay? Yes. Please tell me. Mod Vr1 is less compared to mod Vs. Yeah. Okay. Next thing. Let us take in the second case, that is with series capacitor, what will happen? After keeping series capacitor, what will happen? That will think now. So case two, that is with series capacitor placement, you write with the series capacitor placement. Yeah. See, I will copy this diagram, same diagram I'm copying, right? See this. See, do we have any change in the receiving end side load? Do we have any change in the receiving end side load? No, we don't have any change in the receiving end side load. Okay, listen please. I am adding that series capacitor at some place in the transmission line. At some place in the transmission line, we are adding the series capacitor. How is the impedance of series capacitor? How is the impedance of series capacitor? Plus J or minus J? Plus J or minus J? It will be minus J. So it will be minus J XC. That's the extra series capacitor we have added. On the behalf of that, the receiving end voltage, it will become VR. Receiving end voltage will be modified to VR2, but you don't get any change in the receiving end power factor. Okay. What about the current flow in the line? Will it be remain same or getting changed? What about the current flow in the transmission line? Will it be remain same or going to be changed? Anybody please tell me. Tell me please. What about the current flow in the line? See, listen now. For example, if you talk in this manner, this line impedance is Z line. Line impedance is Z line, I am writing. Okay. Load impedance is Z load. Load impedance I am calling as Z load. Kindly observe. We have a line impedance of Z line, load impedance of Z load. How will be that line impedance value compared to load impedance? Practically speaking, how will be the line impedance value compared to load impedance? Line impedance value compared to load impedance. It's very, very less, right? Very, very less. Line is having very, very less impedance compared to the load impedance. So if that is the case, please listen kindly, don't confuse. Listen kindly. If that is the case, even though you are adding that series capacitor, there is a change in the line impedance only. A small change in the line impedance only, but the overall impedance of the circuit is commanded by whom? Load impedance only. As a load was not changed, the overall impedance will be more or less same. So that current flow in the line will be almost same as of the case 1 value. Okay, right. Serious one. As Z line is very, very less compared to Z load, due to the addition of series capacitor, due to the addition of the series capacitor, Z line will be changed. But overall impedance will be almost same. So magnitude of current is almost same. Even after adding that series capacitor. It will be almost same value, we can say constant. It will be almost same. Okay, now I can take up this mod Vs minus mod Vrp expression. Okay, before moving to that, let us make this comment also. All of you, please tell me. Stop writing, please. Stop writing. You know, overall impedance means line impedance plus load impedance, total number, total number. If you know total impedance of the circuit, what is power factor? If you know the total impedance of the circuit, power factor will be total resistance value by magnitude of the jet total. Getting this? Total resistance value by magnitude of the jet total. Okay, R by Z. See, R total is almost same, na? Resistance value of the circuit, total line and load is almost same. But what about the jet load? It is decreasing by little. Yes or no? Because of this minus Jx. So jet total will be decreased little bit. So cos phi will be little improved. A small improvement, negligible improvement in the power factor can be expected because of this series capacitor addition. All of you getting this word? Means, for example, let's say initially before adding the series capacitor, I have a power factor, let's say 0.8 lagging. After adding series capacitor, it may come 0.85 or 0.81. Like that, we are going to get a small increment in the power factor. Okay. So series capacitor addition, I am writing that statement here itself. Series capacitor addition may cause for a little improvement in power factor only. Little improvement in the power factor only. So I can't use this series capacitor as a power factor correction device. We can't use it as a power factor correction device. So series capacitor can't be used as a power factor correction device. Can't be used as a power factor correction device. Okay, done. Next thing. So let's take up that mod Vs minus mod Vr2 with series capacitor placement. Let's take that Vs minus Vr2. So I said current is almost same already. Current is almost same as compared to earlier case. Now we write mod I into RL into cos phi r. First term you get like mod I into RL into cos phi r first term. And you have a lagging load, so it is plus. Mod I into what is the reactance? XL minus XC. Reactance will be XL minus XC into sin phi r. Sin phi r. Let's modify this one and we will replace the first term in this and we will conclude it. So let's say here mod I into RL cos phi r plus, here I into XL into sin phi r. Okay. And you have minus mod I into XC into sin phi r. Like this you can say. And the first two terms summation. First two terms summation is mod Vs minus mod Vr1. Mod Vs minus mod Vr1. That will be the first two terms summation. Mod Vs minus mod Vr. Let's move ahead. Let's move ahead by taking Vs minus Vr2. By taking that mod Vs minus mod Vr2 here is equal to mod Vs minus mod Vr1 minus mod I into Xc into sin phi r. Mod I into Xc into sin phi. Like that you can get. Like that you can say. Yeah. Now that mod Vs will be cancelled out on both sides. So you can get mod Vr2 equals to negative of mod Vr1 minus mod I into Xc into sin phi r. From this you can say the receiving end voltage mod Vr2 will be equal to mod Vr1 plus I into Xc into sin phi r. So from this you can say mod Vr2 is greater compared to mod Vr1. From this we can say mod Vr2 is greater compared to mod Vr1. Mod Vr2 greater than mod Vr1. So definitely there is a rise in the receiving end voltage magnitude because of the series capacitor addition. Particularly which load we are discussing now? Lagging load we are discussing. Lagging load we are discussing. Okay. Yeah. So next, if you see, for example, if you have a leading power factor load, what will happen? Very simple thing. Very simple thing. I will show in the next slide. Next slide, right? If load is leading in nature. How will be your first equation? Means this one. This one. How will be your first equation? This Vs minus Vr1 without series capacitor placement. So you can say case one will give an equation for you something like this. An equation you are going to get something like this, but here we get a minus sign. Here we will get some minus sign. Okay, what about case 2 with series capacitor? What you can write? Case 2 with series capacitor. This is the equation we have. Let me copy this one. Right, Vs minus Vr2 equal to I into RL. Something like this you are getting, but here you get a minus sign. Here you will get a minus sign. And if you expand this, finally what you can get is Vs minus Vr1 plus I into Xc into sin phi r. I into Xc into sin phi r you can say. And do that cancellations. Vs is cancelled out and you will get now Vr2 will be equal to Vr1 minus I into Xc into sin phi r. I into Xc into sin phi r. All of you getting this? Please tell me. Mod Vr2 equals to mod Vr1 minus I into Xc into sin phi r. There you can observe that Vr2 is less compared to Vr1. So if the load is leading in nature, definitely there is a fall in the receiving end voltage magnitude after adding the series capacitor. And if the load is lagging in nature, there is a rise in the receiving end voltage magnitude after keeping the series capacitor. I think all of you have understood these statements, what I said. Is it clear, all of you? Please tell me. Please tell me, all of you clear about this one? Sir, no? Yes? Okay, done. Next thing. Next thing. See, actually, what the series capacitor is doing simply is if you have a low voltage at the receiving end side, if you have a low voltage at the receiving end side, it is attempting to raise the voltage magnitude after addition. If you have a over voltage at the receiving end side, and after adding the series capacitor, that voltage is decreasing. Means always this series capacitor will try to make the receiving end voltage close to sending end voltage. It will try to make always the receiving end voltage close to sending end voltage. Following all of you? Tell me please. If you have over voltage at the receiving end side, it will decrease the voltage. If you have under voltage at the receiving end side, it will increase the voltage. Okay. What shunt capacitor will do? This is a place where you should get a difference. What shunt capacitor will do? Increase the voltage. That's it. Shunt capacitor will increase the voltage. Even though there is a over voltage, add shunt capacitor bank, it will increase the voltage further. Following. What shunt reactor will do? Decrease the voltage. It will decrease the voltage. Means even though there is under voltage, add the shunt reactor, it will decrease the voltage further. But series capacitor is not like that. Series capacitor is not like that. If there is a over voltage, it will decrease it. If there is an under voltage, it will increase it. Following all of you. That's why series capacitor itself will do both the duties of controlling under voltages as well as controlling the over voltages in the system. Okay, next. Some more terms. Let us discuss about the series capacitor. Some more terms. See, what is the amount of reactive power delivered by the series capacitor? Amount of reactive power delivered by the series capacitor. That will be I square into XC. I square into XC. Okay. Yeah. So I'll write first statement. Q delivered by series capacitor. Q delivered by series capacitor. Right. QSE per phase. That is simply magnitude of current square into series capacitor reactance. And three-phase value will be 3 times of this. Simply 3 into magnitude of current square into series capacitor reactance. That's the Q delivered by the series capacitor. Next statement. Very simple. Very simple. Think about the lagging load only. This leading load I kept in a bracket completely. Leading load I kept in a bracket completely. We are not discussing about leading load now. We are taking up lagging load only. What is that magnitude rise in the voltage you got now? What is that magnitude rise in the voltage? Magnitude of I into XC into sin phi r. That's it. Approximately. It's not exact number. This is not the exact analysis what we are doing. It's approximating. Okay, right. So magnitude rise in the voltage. Magnitude rise in the voltage. Due to series capacitor, I can say it is delta VC equal to mod VR2 minus mod VR1. And we are talking this with respect to lagging load only. Magnitude of current into XC into sin phi r. Magnitude of current into XC into sin phi r, you can see. Okay, done. Next. Let's modify this equation a little bit. Multiply with the current and divide with the current. Multiply with the current and then divide with the same current. Now you see, what is that I square into XC? That is QSE, series capacitor reactive power supply. So QSE, or you write like this. Better. Q series capacitor into sin phi r by current magnitude. Sin phi r by current magnitude. Q series capacitor into sin phi r by current magnitude. That is the magnitude voltage rise we are going to get because of the series capacitor addition. Okay, next thing. So next, let's take up like this. Some consequences we have studied till now due to series capacitor. One, it is decreasing the overall series impedance, or you can say overall series reactance. Okay. Next thing, it is controlling the voltage. That's one thing. But it won't cause for any improvement in the power factor. it may not cause a great improvement in the power factor. Now we are going to discuss about some major consequences, some of the major consequences of the series capacitor placement into the system. Okay, yeah. So I'll take that heading as major consequences due to series capacitor placement. I'll say consequence number one, major consequence number one. Major consequence number one. Simple, very simple. Major consequence number one. See, in the case one, we have simply one line here with an impedance of JXL. Sending end side, we have VS. Receiving end side, you call it VR1 for time. VS, VR1, JXL is a series impedance. JXL is a series impedance. What is maximum power transfer capacity of this one? Formula for the maximum power transfer capacity, that is Vs into VR1 value by series reactance, that is only line reactance we had now, that is XL. We had only line reactance, that will be XL. Simple. Now if we had series capacitor, what will happen? Overall reactance will decrease. Na? If overall reactance is decreasing, Pmax value definitely increases. So maximum power transfer capacity of system is expected to be increased. So this is your sending end voltage, and receiving end voltage might be some value VR2, but VR1, VR2 will be a bit close only. But definitely there is a change. Definitely there is a change. There may be a rise or fall, whatever it is. Okay. So you can say line impedance is JXL. The series capacitor impedance is minus JXC. And then maximum power transfer capacity of this will be PS into VR2 by XL minus XC. XL minus XC. So there is a decrement in the overall reactance of the system, series reactance, that causes for increment in the. So Pmax2 is greater compared to Pmax1. Pmaximum 2 is greater compared to Pmaximum 1. Or else series capacitor placement will improve the system stability. Series capacitor placement will improve the system stability. System stability increases. System stability increases. It will be improving the system stability. That's why most of the times we used to call this series capacitor as a stability improvement device. It will be called as stability improvement device rather than the voltage control device. Okay? Because this is a dominant feature of the series capacitor placement. Strictly speaking, it's a dominant feature of the series capacitor placement. So practically series capacitor called as stability improvement device. Stability improvement device. Stability improvement device. Okay, done. Next thing. So this is one major consequence, improvement in the stability of system. Second major consequence we are going to discuss now. Second major consequence of series capacitor placement. Second major consequence of series capacitor placement. Yeah. So I'll take again case 1, case 2 without series capacitor and with series capacitor. Case 1, let's assume we have a voltage source here. Voltage source, and this is a line. Line impedance, I am calling it is JXL. Line impedance I am taking as JXL. Sending end voltage is Vs at an angle 0. Sending end voltage is Vs at an angle 0. Now, listen, please. I have taken a fault at the end of the line. You assume this is a single phase system and it's a single phase fault. Single phase system, it's a single phase fault. Simple. We have a voltage source connected with a series impedance. At the end, you have a short circuit. How much amount of current flow in the loop you have? That is source voltage by impedance. Source voltage by impedance. I need only magnitude. I need only magnitude. So magnitude of that fault current IF1 is nothing but Vs by XL. Vs by XL. That is a fault. IF1 fault current magnitude is mod Vs by XL. Mod Vs by XL. Second case, I think most of you might have getting this one. Might be getting this one. Voltage source. We have a line and series capacity is added to this. Okay. So this is the series capacitor addition we have. Series capacitor impedance is minus JXC. Line impedance we are calling as JXL. And this is the fault location. And current is IF2 here. IF2. And what is the magnitude of the fault current you can get here? That is sending end voltage Vs by, you can get now XL minus XC. XL minus XC we are going to get. So that XL minus XC, of course, less compared to XL. XL minus XC value was less compared to XL. So IF2 will be higher compared to IF1. So fault current magnitude was increased. That's the comment you should make. After adding series capacitor, fault current magnitude was greater compared to without series capacitor condition. Fault current magnitude was increased. Else you can say fault level in the system was increased. Fault level in the system was increased, we can say. Fault level in the system was increased. Fault level in the system was increased. Is it an advantage or disadvantage for you? Fault level increment in the system. Is it an advantage or disadvantage? Definitely it is a disadvantage. Definitely it's a disadvantage. Why it is so means? Generally, we will be keeping one circuit breaker to interrupt this fault current. Right? And here also I will say circuit breaker we are keeping to interrupt the fault current. You see, the first breaker has to interrupt a current of IF1 magnitude. Second breaker has to interrupt a current of IF2 magnitude. So the circuit breaker requires to have high breaking capacity. It has to interrupt high breaking current. So obviously the cost, size and cost of the circuit breaker definitely gets increased after the addition of the series capacitor to the circuit. Okay, right. So as the fault level is increasing, circuit breaker requires to have more breaking capacity. More breaking capacity. Requires to have more breaking capacity. That implies size and cost of circuit breaker. Size and cost of circuit breaker increases. Size and cost of the circuit breaker will be increased. This is one of the potential disadvantage. Next thing. One more thing. I will tell in a general way. Just think about this one. Keep these statements aside. Whatever I am discussing. Some simple statements I am going to make here. Number one, series connected device. Next one is a shunt connected device. Generally, these two, series connected device, and the second one we are going to call as shunt connected device. That's okay. Result case. See, actually, if you are designing one device to be kept in series with the system, all of you stop writing. Just look. If you are designing one device to be placed in series with the system, that device should carry system current all the time. Yes or no? If I am designing one device to be placed in series with the system, that should carry system current all the time. Yes or no? Yes, it should carry the system current all the time. Okay. See, means obviously it should have high current rating. Maybe in the order of kiloamperes also you can say high current rating. See, if you are designing the device with a high current rating, voltage rating of the device required must be less. Voltage rating of the device, we are going to keep it as less, then only we can keep some power limit on that apparatus. Okay, so series connected device should have high current rating. We have to design it for high current rating. So definitely we should take up a low voltage rating for this. Low voltage rating for this one. Rating. Shunt connected device, I can say now. Shunt connected device. Shunt connected device. You see, if it is a shunt device, we are keeping that in parallel with the system. It should have high voltage rating, definitely. It should have high voltage rating, definitely. So if you are designing that with high voltage rating, definitely you should keep the current rating of the device as low. Okay. So shunt connected device should have high voltage rating because it is experiencing system voltage, because it is experiencing the system voltage. That's why. And it should have low current rating. Low current rating. Okay. So these are the basic properties. These are the basic properties of the series and the shunt connected devices. Series and the shunt connected devices. Okay. Yeah, all of you getting this one? What I discussed here? All of you getting it? Please tell me. Please kindly respond. All of you getting it? No, low resistance, high resistance, that low impedance you talk, low impedance, high impedance you talk, you want, not with respect to resistance. Okay, let's continue. Let's continue now. See, this is a series capacitor we have added. Series capacitor. What is the property of the series capacitor with respect to ratings now? What will be the property of series capacitor with respect to ratings? It will have high current rating, but it will have a low voltage rating. It will have a low voltage rating. But you see, during that short circuit fault, what is the magnitude of voltage appearing across series capacitor? VC. What's the magnitude of voltage across series capacitor? IF2 magnitude into XC. IF2 magnitude into XC. So the voltage magnitude across the series capacitor is becoming very, very large because fault current is very high. Because fault current itself is very, very high. Because of that, we have a large voltage gap across the series capacitor that may definitely exceed the rating of it. That may definitely exceed the rating of it. Because of that, there is a damage for the series capacitor possible. Right? So I can say here, so during short circuit fault, voltage across series capacitors, voltage across series capacitor, VC magnitude will be fault current magnitude multiplied with XC. Fault current magnitude IF2 multiplied with XC. Okay, but as IF2 is very, very high here, IF2 is very, very high, VC will be also very high because of large value of VC, because of the large value of VC, there may be a possible damage for series capacitor. There may be a possible damage for the series capacitor. Okay? There may be a possible damage for the series capacitor. See, is it a disadvantage or advantage for you? Is it a disadvantage or advantage? So this complete consequence, whatever I am discussing now, that will be a disadvantage only. Because fault level in the system is increasing, we have to modify the breaker, we have to change the breaker with high capacity. Not only that, the capacitor itself is damaging. It's a complete disadvantage for me. Okay, at least, how to overcome the damage of the series capacitor? How to overcome the damage of the series capacitor? You please tell me, series capacitor is getting damaged because of overcurrent or over voltage? Tell me please. Series capacitor is getting damaged because of overcurrent or over voltage? Over voltage across it, not over current. It is due to over current in the line causing over voltage across capacitor. That is leading to damage, right? It is causing, so it is damage due to over voltage. Okay, okay. Over voltage. Is it abnormal or normal? Means, is it abnormal or steady state? Is it abnormal condition or steady state condition? It's an abnormal condition. It's an abnormal condition, not under steady state. See, if you have an abnormal over voltage, are you going for controlling of that voltage or protection? If you have an abnormal over voltage, are you going for controlling of that voltage or are you going for protection? We have to go for protection. We have to go for protection. Means we have to provide a protection for series capacitor from these over voltage damages. Okay. Therefore, to avoid this damage, a over voltage protection shall be provided for series capacitor. A over voltage protection shall be provided for the series capacitor. Yeah. See, one of the simple and basic over voltage protective device will be sphere gap. Let's discuss little about that sphere gap. Very simple in operation. Sphere gap. It's very simple in operation. Yeah, it can be called sometimes as spark gap also. Spark gap, or you can call it as sphere gap. Any name. Simple, very simple. See, these are two spheres with some spacing. Maybe solid spheres or hollow spheres, doesn't matter. Most of the time, solid spheres only, if it's of small size. These are the two spheres with some gap. And this is that D, what we are calling. This is that D gap. And you are applying some voltage here across the sphere gap as V. We are applying some voltage here, V. Simple, very simple discussion. If that voltage applied across the gap is low, then electric field intensity across the gap is low. Okay. Once after saying that the electric field intensity is low, I can say gap will be remains open. No ionization for the gap. No ionization for the gap, you can say. And similarly, if that applied voltage is high, electric field intensity will be high. There may be a chance of getting ionization for the gap. There it will act as a short circuit. So if the V is high value, and electric field intensity is high value, so gap gets ionized. So it is a simple operational phenomena of the sphere gap. So whenever that gap gets ionized, it will be acting as a short circuit with zero resistance, right? So in the first case, resistance of the gap is infinite, whereas in the second case, the resistance of the gap is approximately zero. Second case, the resistance of the gap will be approximately zero. Yeah. So completed. Tell me please. So simply what you do is, whatever the sphere gap we discussed now, that you connect across the series capacitor. This sphere gap you have to connect across the series capacitor. So the sphere gap is connected. Sphere gap was connected across series capacitor for its protection. Across series capacitor for its protection. Across series capacitor for its protection. Okay, next. So let's show the two things here. Sphere gap added, normal condition, abnormal condition. and I will close this point after discussing about it. Okay, so I'll say case one, normal case without any fault. This is the series capacitor we have, and spare gap we are adding something like this. Spare gap we are adding. Normal condition, normal condition. Second case, we will say abnormal case or fault case. Faulted case, we will write here, faulted case. Right? Just look here, first case. No fault on the system. We have some current flow I, and voltage across series capacity is normal value only. All of you listen please, We have some normal current flow in the system. Voltage across series capacity is a normal voltage only. That voltage will appear across a gap. So gap will not ionize. No ionization. No ionization for the gap. And that current will continue to flow something like this. Current will continue to flow something like that. Right? And you see this. And gap current will be zero. Gap current will be zero. Now, if there is a fault at some place. Right. So this current is very large fault current. Current is very large, that we are saying as fault current. Because of high fault current flow, voltage across series capacity is very, very large number. Voltage across series capacity is very, very large number. Because of that large voltage, definitely this gap is going to be ionized. Right? Ionization. See, whenever the gap gets ionized, whatever the fault current we have, that will be diverted through spare gap. And you don't get any current in this capacitor. So our capacitor will be completely safe from damages. Whatever the fault current you say, that will be diverted through spare gap. Okay. So this is the second major consequence of series capacitor placement. And we will see third major consequence. It is one of the major one compared to all, of course. Major consequence number 3, I am writing. Major consequence number 3. Major consequence number 3. Look please. It is a generator here connected to a line and a series capacitor. At the end, we might be having a load. And this is our generator. Yeah, presently we are using the spare gap. Across the series capacitor for protection. Now, look here, please. This is RL, and this is JXL, and this is minus JXC, and this capacitor is an extra addition we are making. RL and XL are natural elements of transmission line itself, and JXC we are adding VV. See, just by looking at the circuit, what we'll feel? We have a RLC series circuit. We have a RLC series circuit. So if you have a RLC series circuit, what comes in our mind generally? Resonance. There is a possibility of getting resonance in this circuit. Okay. Assume that your load is UPF. Means it's a pure resistor. So LC elements exist only in the transmission line. Because of this L and C, there is a possibility of getting resonance. Okay. At how much frequency we are going to get the resonance? Yeah. Please look here. Resonant frequency. I'll call it is FR. FR is equals to, formula for this is 1 by 2 pi root LC. 1 by 2 pi root LC. That is a resonant frequency FR. Resonant frequency FR is equals to 1 by 2 pi root LC. Next thing. Look here, please. That L is a line inductance we have chosen. C is a series capacitance what we have added. I will be modifying this one. So let us say with frequency, I will multiply in the numerator and denominator. So 2 pi f you get in the denominator. So it will be omega. So it will be root LC. So it will be like f by square root of omega L into omega C. And it will be f by that omega L is nothing but XL. Omega C is 1 by XC. So it will come like f into square root of XC by XL. This is the resonant frequency formula. Resonant frequency equals to f into root of XC by XL. What is that f here? F is the operating frequency of the system, maybe 50 Hz. F is the operating frequency of the system, maybe of 50 Hz, and resonant frequency equals to f into root of XC by XL. XC is the series capacitor reactance. XL is a line reactance. Okay, yeah, done. Next. Generally, if you talk about this XC by XL, we discussed, I think, in the compensation. Yes or no? We have discussed about that in the compensation. What is this ratio we have to? Degree of series compensation. KSE. Degree of the series compensation, we said that name as KSE. Is it correct or not? All of you remember this? Please tell me. Degree of series compensation, KSE. So the resonant frequency FR is equals to f into root of KSE. Root of KSE. Resonant frequency FR equals to root of KSE into F. So practically speaking, that resonant frequency, the KSE, degree of series compensation, is less than 1, right? So as KSE is less than 1, you can say that the resonant frequency will be less compared to actual frequency of the system. Resonant frequency will be less compared to actual frequency of the system. FR will be less compared to F, you can say. Okay, all of you getting this one? All of you getting this? FR will be less compared to F. Next thing. Means, for example, if the frequency of supply is 50 Hz, frequency of operation is 50 Hz, resonance will occur for a frequency lower than 50 Hz. Okay, one more simple network theory concept I am asking you. Tell me, when we get the resonance in the system, simple network theory answer I want. When we will get resonance in the system? Anybody, please tell me when we will get the resonance in the system. XL equals to XR is okay. Yeah. Next, XL equals to XC. Next one. Any other condition of getting the resonance? See, simply, whenever the supply frequency equals to resonant frequency of the circuit or natural frequency of the circuit, whenever supply frequency is equals to natural frequency of the circuit, at that time, we are going to get a resonance. Yes or no? But your resonant frequency is very less and your supply frequency is 50 Hz. There's a great gap. Between them. Because of that, there may not be a possibility of getting the resonance under normal operating conditions. Under normal operating conditions, you may not get it. But maybe in some times of abnormal conditions, load changes. At those conditions, there is a possibility of getting the resonance in the system. Okay, yeah. So I can say here, but there is a possibility. There is a possibility of getting resonance. In abnormal conditions. Or you can say disturbance timings. Disturbance conditions. In abnormal conditions, or you can say disturbance conditions, we used to get this resonance. I'll tell you, just listen to me. See, whenever there is a disturbance on the system, just look here. Disturbance occurred, I'll say. Disturbance occurred on the system. See, during the disturbance, we have transient currents. We have transient currents. We have DC transient as well as AC transient, both now. Fundamental current will be there. Look all of it. 50 hertz current will be there. DC transient is there. There is another transient called as AC transient, which will be happening at a frequency of 1 by 2 pi root LC. 1 by 2 pi root LC. So called the resonant frequency of this circuit. So during disturbance, you call this is IES, system current. That's the meaning. ISYS, system current will be like this. Okay, normal AC current, steady state current, you can say, plus DC transient, plus we have one more current as AC transient also. This AC transient, it is at FR frequency. This does not have any frequency. But this AC current, what you said, is at a frequency of F only. What we said, 50 hertz. So 50 hertz current is there. DC transient current is there. FR frequency current also existing because of this LC. Because of that L and C combinations. Yeah, listen now. See, this AC current transient, whatever it is getting created at FR frequency might create a rotating magnetic field in the air gap. Of this machine. That may create a torque. Yes or no? Right. Listen please. So from this you can write IACT creates RMF and causes for torque in the air gap. Causes for torque in the air gap. I'm attempting to make this one a bit simple. Just listen now. Just all of you stop writing. Just if you look at fan or a motor, fan, whatever it is, or generator, whatever it is. If that rotor is rotating, will you say it's a perfect and smooth rotation? Or can you observe any shake the operation? Definitely, it's not a smooth rotation. It will be a type of shaky operation. Those oscillations we call as torsional oscillations. Any rotating body, because of some effect, because of some reason, will make some torsional oscillations. Right? Torsional oscillations exist in any rotating body. In any rotating body, we will get the torsional oscillations. Yeah, please listen. Please listen. If the frequency of this torque created now, extra torque, frequency of this extra torque created and frequency of these torsional oscillations, if these two are matched, frequency of the torque created and frequency of the torsional oscillations, if these two are matched, what we can experience now? What we can experience now? Tell me please. Those torsional oscillations will grow. Torsional oscillations will grow. Magnitude of the torsional oscillation will increase. That may cause an undisturbed operation of the rotor. Undisturbed operation of the rotor that may cause for some sort of mechanical damage in the system. That may cause for some sort of mechanical damage in the system. Okay, so I'm writing that statement. Kindly go through it. The frequency of torque created if the frequency of the torque created matches with torsional oscillation frequency, then the torsional oscillations will grow. Listen please. So whenever these torsional oscillations are becoming severe, if you think about your mechanical system, we have a rotor body, shaft, turbine. Rotor body, shaft, turbine. Which is weakest one among the three? In the generator? That will be shaft. Shaft will be the weakest one. So that shaft is going to experience some sort of mechanical damage. This we are going to call it as shaft fatigue in the alternators. Okay, torsional oscillations will grow and causes for severe damage. Severe damage for shaft. For the shaft, this is going to be called as shaft fatigue in the alternator. Shaft fatigue in the alternator. So prime mover failure also we will call sometimes. It can also be called as prime mover failure. Okay. Yeah. So this is one of the major disadvantage of the series capacitor placement. Actually, we the people don't know about all these things here. But one thing we know that by adding the series capacitor, maximum power transfer capacity increasing, fault level is increasing, we have to modify the breaker. The people know only about these things. Okay. And then with those advantages, the people have gone for the installation of the series capacitor. Okay. So after installing the series capacitor, after some time, the nearby the alternator shaft was broken. For the first time I am saying long back, after they are keeping the series capacitor, nearby generators shafts was damaged. Then they have a question that why these shafts were damaged after keeping series capacitor. Then they have analyzed that in this manner and they have introduced a term called as sub-synchronous resonance in the system. Because you know the resonant frequency is less than actual frequency of system. So this type of resonance we are naming as sub-synchronous resonance in the system. Yeah, who will be causing for the sub-synchronous resonance in the system? Series capacitor placement. And if there is a disturbance, creates AC transient current, something like this. And that will be producing some torque. Right. If the frequency of the torque matches with the oscillation frequency of the rotor, torsional frequency of the rotor, then the shaft is going to be damaged. This phenomena we call as shaft fatigue in the alternator. This is one of the major disadvantages of the series capacitor placement. Yeah. The cause for torsional oscillations we don't know due to some reason, maybe air effect, slots, uneven air gap, whatever it may be, some reason, some reason. Yeah, okay. So this is about series capacitor placement. Let's discuss one small problem on this one, and then we'll move with the comparison between the series capacitor and the shunt capacitor placement in the system. Very, very small problem we'll discuss. So you go through this one. Series. Still we are using the series capacitor by going for some sort of control. We'll be converting that into a FACTS controller and we are using it. Okay, it batch means numbers only, no? Those are numbers only. FR is a number, mechanical frequency is a number. What's the meaning of matching that? Series capacitor is the main reason. Series capacitor is the main reason for this subsynchronous resonance. Okay, please check this one. A lossless transmission line has its maximum and ideal power transfer capacities P1 and P2 respectively. P1 and P2 respectively. If a 40% series compensation was provided to the line, the modified maximum and ideal power transfer capacities will be capacities will be dash respectively. I've given some options here. Check the thing quickly. Check the thing quickly. See, in the problem he is saying that the line is having ideal, sir, maximum and ideal. What do you mean by maximum? P max. What do you mean by ideal? What do you mean by ideal power transfer capacity? Anybody? What do you mean by ideal power transfer capacity? SIL. SIL. So I'll say here. P maximum in the first case is P1. SIL in the first case is P2. Okay. Then please tell me, if 40% series compensation is provided, what will happen to P max value? What will happen to P max value? Look here. Degree of series compensation is 0.4. 0.4. Let us take P max 2 with series capacitor. It will be Vs into Vr. Approximately, I'll say same voltages. But in the denominator, you should keep XL minus XC. You should keep that as XL minus XC. That is nothing but Vs into Vr, and you take that XL common. By taking XL common, you get 1 minus XC by XL. Means you can get here, Vs into Vr by XL is what? Anybody? What is it Vs into Vr by XL? That is nothing but P max 1 only. Vs into Vr by XL, that is a P maximum 1. So it is a P maximum 1 by 1 minus, what is XC by XL? 0.4. This is XC by XL value, 0.4. So it is P1 by 0.6. P1 by 0.6 means 1.667 times of P1. That is a P maximum 2N, maximum power transfer capacity after providing the series compensation. 1.667 times of P1. This is a P maximum calculation. Next, we think about SIL calculation now. Next, we'll think about the SIL calculation, surge impedance loading calculation now. Let's say, what is SIL2 formula? SIL formula is generally V square by ZC, na? But here I should write ZC2. What is ZC2? What is ZC2 formula? It is ZC1 into root of 1 minus KSE by 1 minus KSH. This we have discussed already. Root of 1 minus KSE by 1 minus KSH. So this is nothing but ZC1 into square root of 1 minus KSE 0.4, 1 minus KSH. It didn't give in the problem. It didn't said about the shunt compensation, so it will be taken as 0. So it is root 0.6 times of ZC1. So surge impedance loading in the second case will come to be mod V square by ZC2 means root 0.6 into ZC1. What is mod V square by ZC1? What is mod V square by ZC1? SIL1. Mod V square by ZC1 is SIL1. So it is SIL1 by root 0.6. SIL1 by root 0.6. SIL1 is P2, P2, P2. What is root 0.6? What is that? 1 by root 0.6. 1 by root 0.6. I think 1.25 something. 1.29. Good. 1.29 times of SIL1 I am replacing with P2. SIL1 I am replacing with P2. These are the Pmax2 and the SIL2. Just check back. That is option D. Option D is correct. 1.67 P1 and 1.29 P. So correct answer from the options given will be D. Correct answer from the options given will be D. Next. So next we are taking the comparison between series capacitor and shunt capacitor. Mainly I will take up two comparisons. One. Voltage profile comparison is one. Voltage profile comparison one. Means voltage profile improvement. Second one, rating of the capacitor bank comparison. Comparing the ratings of the capacitor banks, particularly reactive power ratings comparison. Okay, let's say first one. Voltage profile comparison. Voltage profile comparison between series and shunt capacitor, or shunt and series capacitors. Right? Voltage profile comparison between series or shunt and series capacitors. Yes. Done. Let's look here. Let's look. I'll take two cases. First case, shunt capacitor. Second case, series capacitor. Two diagrams I'm sure. Two plots in fact. First one, shunt capacitor. Shunt capacitor. Second page I am taking. Second page, series capacitor. Series capacitor. Next, listen. See, we have to plot that voltage profile. Starting from sending end side to receiving end side, I have to check how that voltage is varying point by point. That we should keep in a plot. That's the voltage profile. See, to know that voltage at each and every point on the line, we have to take the distributed model of the line. Okay, yeah. So let's say we have a source here. And we are neglecting shunt element in our analysis. Let us convert the total series impedance into number of sections. So it is series impedance 1, 2, 3, 4, 5, 6, 4, 5, 6. So like this we have series impedance. Each and every impedance value is equal. Z, some number, whatever it is, Z, equal number. Z is a each and every impedance value. And this is a receiving end side. We are keeping a lagging power factor load here. Lagging power factor load. Okay. And we have some current flow in this line as I. And sending end voltage, I will say Vs, and you have a receiving end voltage of VR. Sending end voltage Vs, and we have a receiving end voltage of VR, you can say. VR. Yeah. Now let us show the plot. Let us show the plot. It is an axis on which we are going to show voltage. It is an axis on which I am going to show length of line. Length of line. Right. So on this axis, I am showing the mod V, and this is the length of line. And let me show sending end side and receiving end side. This is a sending end side. Yes, I am showing. And it was a receiving end side. I'm calling it is R. Sending end side, receiving end side, yes, R. Next, listen. All of you stop writing, stop writing. This is sending end voltage magnitude mod Vs. Sending end voltage magnitude mod Vs. Okay, if you find voltage at this place, it is Vs minus I into Z now. This point voltage will be Vs minus I into Z. So that voltage will be definitely low compared to Vs value. This point voltage will be low compared to Vs value. What is the voltage here? Vs minus I into 2Z. I into 2Z. Drop was more, so resultant voltage will be lesser. And if you calculate voltage here, Vs minus I into 3Z. Drop is more, again voltage will be low. Like that, what we can experience is continuously starting from sending end side towards the receiving end side, voltage decreases. Definitely, it's a non-linear variation. Definitely, it's a non-linear variation. But for my convenience, I am showing that as a straight line. For my convenience, I am showing that as a straight line. Like this, you can expect. And this is our voltage without series capacitor placement. Sorry, without shunt capacitor placement, VR1. This is the voltage at the receiving end side without shunt capacitor placement. That is VR1. So these are the voltages at various locations on this line. Okay. Like this. Next. Whether this voltage profile is good or not. How to decide? How to decide whether this voltage profile is good or not? By comparing this with a flat profile. By comparing this with a flat profile, you should say, is it a good profile or not? Yeah. So I will be showing that flat profile for you. Flat profile. Maybe that flat profile line is nothing but your VS line only. VS line only. So whatever this VS line here, that is a flat profile just for the reference sake. Just for the reference sake, I am drawing it. Flat profile. Flat profile. Listen all of you, please. Listen all of you. This is a voltage profile I am saying without keeping shunt capacitor as well as without keeping series capacitor also, right? Without keeping any element, just we have shown the profile. That profile itself is a profile without shunt capacitor as well as without series capacitor. Okay, let us take up the same graph to the next case also. Series capacitor case also. I will be showing the same graph. Same plot you repeat for the next case also. So here you write, this is without series capacitor. Without series capacitor. And here you write without shunt capacitor. Without shunt capacitor. Without series capacitor, and that is without shunt capacitor. Yeah. Okay, you can draw the diagram later, that second diagram, series capacitor diagram. Just listen now. Listen now. I am adding a shunt capacitor bank here. Adding the shunt capacitor bank. After adding shunt capacitor bank at the receiving end side, what will happen to current value? All of you, please tell me. All of you, please tell me. All of you, please tell me. What will happen to current value? Decreases, na? Current value will definitely decreases. Yes or no? That's what we have shown in the phasor diagram also. That's what we have shown in the phasor diagram also. Current value decreasing. Current value decreasing. But your sending end voltage remains same. Sending end voltage remains same. And what is voltage at this place now? What is voltage at this place? Vs minus I into Z. Vs minus I into Z. Current value decrease. Because of decrement in the current, voltage drop decreasing. Resultant voltage will rise up little bit. And this point voltage, Vs minus I into 2Z. Current is less. Voltage drop is less. Resultant voltage will rise up still. Like that. What I'm saying is, the value of current decreases throughout the length of the line. Value of current is decreasing throughout the length of the line. So definitely, there is a rise in the voltage at each and every point on the transmission line. There is a rise in the voltage at each and every point on the transmission line. Why? So that we can say the voltage profile might come more or less like this. The voltage profile might come more or less in this manner. Right? So there is an improvement in the voltage profile. After adding the shunt capacitor bank. So I can say it is with the shunt capacitor bank. With shunt capacitor bank. And this voltage we call it as VR2. That voltage we call it as VR2, mod VR2. With the shunt capacitor bank. Our current reduces we discussed long back, Vishnu. In the phasor diagram we have discussed, no? Yeah. So this is the improvement in the voltage profile we are getting after adding the shunt capacitor at the receiving end bus. Now we should think how that voltage profile improvement we get after adding the series capacitor. Let's think now. I am keeping that series capacitor at the midpoint to have a uniformity, more or less uniformity. So I am keeping that at the midpoint. Okay. So this is that series capacitor we have added. Added like this. To get a good understanding, I'm giving some numbers here. To get a good understanding, I'm giving some numbers. Listen please. I'm giving some numbers to get a good understanding. Look, this is J1. Maybe ohms or per unit. It makes no difference. J1. This is minus J2, series capacitor. Next, continued with line J1, minus J2, like that. Impedances. Very simple question to you. After adding series capacitor, what will happen to current flow in the line? Yeah, bright quickly. After adding series capacitor, what will happen to current in the line? It will be remain same. Again, all of you saying increasing. Already we discussed no in the series capacitor. Sir, no. Current will be almost same even after adding the series capacitor. Current will be same. Now tell me please. All of you listen. Stop writing. Listen. This point, sending end side will be same voltage modulus. Look kindly. What is voltage here? What is voltage at this place? That is Vs minus I into J1. Without series capacitor, will it be same? Series capacitor you remove. Calculate voltage here. What is the voltage? Vs minus I into J1. Add series capacitor. Calculate voltage here. What is that? Vs minus I into J1 only. Na? So your voltage at that point will be remain same. remains same. And Mubin, just go through the previous discussion we have done. Again, you are asking same question. Huh? I discussed already in a clear way. Listen now, listen please. So the voltage at this point will be remains same even after adding the series capacitor. So voltage at this place is remains same. All of you understanding this? Please kindly tell me. All of you understanding this one? Yeah. Next thing. What is voltage at this place? It is Vs minus I into J2. I into J2 is a voltage. Without series capacitor also you will get same. So voltage will be remain same. And here also voltage is same number. But you see, after crossing series capacitor, how is the net impedance causing the drop? After crossing series capacitor, what is the net impedance causing the drop? J3 minus J2. J3 minus J2, that will be J1. Impedance causing the drop. So voltage drop suddenly decreases, resultant voltage will rise up at the point. Resultant voltage will be rising up at the. And again, if you find impedance or voltage drop here, so J3, J minus J2, J1, it will be J2 increased. Impedance will net impedance increased. Voltage drop increases. Resultant voltage will fall down. And again, here also falling. How is the profile now? Anybody please tell me? How is that voltage profile? Don't ask me why the current is same. Don't ask me again why the current is same. I already discussed in the series capacitor discussion. Just turn your pages. Yeah. See, up to the series capacitor location, voltage will be more or less same. At the series capacitor location, voltage will rise up and then again decreases. That's the profile you can experience with the series capacitor placement. So I can say the voltage profile might be, I will draw on this line only. So it will be rising like this. Voltage profile will be rising like this. And then again it starts decreasing. And finally it will be reaching to some value like this. So like this we are going to get that voltage profile. And this voltage I am calling as mod VR. That voltage we are calling as mod VR. Yeah. So this is with series capacitor. With series capacitor. Yeah. So how is that voltage profile improvement after adding shunt capacitor? How is that voltage profile improvement after adding shunt capacitor? It is more or less uniform, right? At all the places there is a rise in the voltage. But after adding series capacitor, you don't have a uniformity in the voltage profile improvement. Okay, so I can write here, we have a uniform improvement in the voltage profile. Uniform improvement in voltage profile. Improvement in voltage profile. Whereas here we have a non-uniform improvement in the voltage profile. Non-uniform improvement in voltage. Improvement in voltage. Non-uniform improvement in the voltage profile. Okay. Yeah. Next. So this is one comparison we are making between the shunt and the series capacitors. Next comparison we are going to make in the view of the comparing the ratings of the capacitors. Okay. So next heading, I can say next heading. comparison between shunt and series capacitors ratings for same voltage boost means voltage increment, I can say voltage boost for the same voltage boost. Comparison between shunt and series capacitors ratings for the same voltage boost. Yeah. Let's see this. Yeah, which profile is good means obviously with shunt capacitor we are getting a good profile. Look here means shunt capacitor. What is the voltage boost we have with shunt capacitor? Delta VC. What is the voltage boost with the shunt capacitor? Just look back and check that formula we have discussed in the yesterday class. I think we have discussed at some place. Let me see once. We have probably 1 minute. I will show that equation to you, and then we will move back to the original discussion. See, what's the formula for Q shunt capacitor? So delta VC, X by mod Vs into rating of the capacitor bank. X by mod Vs into rating of the shunt capacitor bank. Okay. Yeah. So I am showing that. I'm showing that expression now. This is X by mod Vs into rating of the shunt capacitor bank. Series capacitor delta VC. Voltage boost by series capacitor. Just now we discussed, no? Just now we have discussed. What is that? Q series capacitor into sin pi r by I. Delta VC by series capacitor is Q series capacitor into sin pi r by I. So you write sin pi r by I into Q series capacitor. Now simply you make these two equations equal. And you find out the ratio between the Q shunt capacitor and Q series capacitor. That will give the answer. Okay. So for same delta VC, same voltage boost, you can call X by mod Vs into rating of the shunt capacitor bank equal to sin phi r by I into Q series capacitor. And if you take up this ratio, Q shunt capacitor by Q series capacitor, okay, and you will get now sin phi r by I here already existing into mod Vs by X. Now, yeah, please complete it. This is Vs. You take into the denominator, it will come I into X by Vs. So ratio between shunt capacitor bank rating to the series capacitor bank rating. It is sin phi r by mod I into X by mod Vs. What is that I into X by mod Vs? See, I into X is a reactance voltage drop. And this is Vs. Assume it as base voltage. So it will be nothing but sin phi r by per unit reactance drop. Sin phi r by per unit reactance drop. Okay. See, can I say approximately this per unit reactance drop equals to per unit voltage regulation? Can I say this per unit reactance drop approximately per unit voltage regulation? Yes or no? Yes. So I can say this like approximately sin pi r by per unit voltage regulation. Per unit voltage regulation. Per unit voltage regulation. Okay. Generally, you tell me, generally, how is the power factor of system? Generally, power factor of system cos phi r will be 0.6, sorry, 0.8 like na, 0.8. Then how is the value of sin phi r to be expected? 0.6. Sin phi r value to be expected is 0.6. So this number will be almost 0.6, you can say. How is that per unit voltage regulation? How is this per unit voltage regulation range? Generally 0.05 to 0.1. In the range of 0.05 to 0.1. So in that view, definitely this ratio will be greater than 1. Definitely this ratio will be greater than 1. So I can say now, shunt capacitor bank rating to series capacitor rating will be greater than 1. Means you can say rating of shunt capacitor bank is greater compared to rating of the series capacitor bank. Rating of shunt capacitor bank is greater compared to rating of series capacitor bank for the same voltage boost. So I can say it is for same voltage boost. For the same voltage boost, you can say rating of shunt capacitor bank is greater compared to rating of the series capacitor. So obviously, if you are keeping higher rating of shunt capacitor bank, not only voltage boost, we have a power factor improvement also. We have a power factor improvement also. Okay, yeah, fine. And this is the end of almost static devices. Static devices. After break, so have a 5 minutes break, 5 minutes short break. So after break, we'll take one table, and there we will see uh, each static element, what will happen to P maximum, SIL, all these things we'll discuss. And then we will move on to the dynamic devices. Dynamic devices. Okay, 5 minutes break. 5 minutes. So I have resumed the audio, video, and screen. So let's continue now. Let's continue. Yeah. So just take up this table. So I'll say first element, static element to be added. Static element to be added. To be added to the line you say. Transmission line, to the transmission line you say. Okay. Next. What will happen to series impedance of line because of that addition? What will happen to series impedance of line? Static element added to line. Added to the transmission line. What will happen to series impedance of that line? What happens to the shunt admittance of that line? What will happen to characteristic impedance, or you can say surge impedance? ZC, which is root of Z by Y. What will happen? This number. And what will happen to SIL value? So called V square by ZC. V square by ZC. And what will happen to Pmax value? What will happen to maximum power transfer capacity, P maximum? And I'm writing behind this video, that is practical application. Practical application. Kindly note down that practical application of the device, of that element, of that static element. Okay. So first we should say what happens to series impedance. Is it increasing or decreasing or no change? What happens to shunt admittance? Is it increasing or decreasing or no change? What will happen to ZC? Increasing, decreasing, no change. What will happen to SIL? Increasing, decreasing, no change. What happens to P maximum? Increasing, decreasing, no change. That's it. And then finally, practical application. Practical application. First one, first device. Let's write the devices. First one, shunt capacitor bank. Shunt capacitor bank. Anybody tell me what happens to series impedance after adding shunt capacitor bank? The class is up to 9:30 only today. Today the class is up to 9:30. Voltage boost means we are adding the delta VC, not adding. Voltage boost means voltage rise, Shiva. Voltage boost means it's the voltage rise. Voltage rise. Okay, please tell me. Please tell me. Shunt capacitor bank we have added. Shunt capacitor bank. What happens to series impedance of line? Series Z of line, what will happen? Tell me please. Series Z of line, no change. Because we are adding a series element, no. As we are adding series element, there is no change in the, shunt element. We are adding shunt element. So there is no change in the series impedance value. So I can say it's no change. No change in the series impedance. What happens to shunt admittance? Shunt admittance value? Shunt admittance. See, natural shunt element of line is capacitive. Natural shunt element of line itself is capacitive. Okay. But we are adding extra capacitor bank now. So the overall shunt admittance value increases. Overall shunt admittance of the line increases. ZC. If that Y is increasing, ZC decreases. Y is increasing means ZC is decreasing. If ZC is decreasing, SIL value increases, which is V square by ZC. SIL value increases, that is V square by ZC. V square by ZC. What happens to Pmax? What happens to the value of Pmax? See, you know Pmax equation, I'll write here. P maximum equation. I'll write in the heading itself better. P maximum equation is mod Vs into mod Vr by series reactance of the line. Series reactance of the line. See, as you don't have any change, listen please. As you don't have any change in the series element, Pmax will be more or less same. But there is a small increment in receiving end voltage. There is a small increment in the receiving end voltage. Because of that, a small increment occurs in the Pmax value also. So a small increment in the Pmax value occurs. small increment in P maximum value occurs. P maximum occurs. Right? A small increment in the P max occurs due to mod VR increment. Due to mod VR increment. Series reactance is more or less same. A small increment is expected in the P maximum because of the what we call shunt capacitor bank addition. Shunt capacitor bank addition. Next thing. Second one you can say. Second one. Series capacitor addition. Second one is series capacitor addition. Series capacitor. Tell me all of you quickly. Very simple. Series capacitor. What will happen to series impedance of line? Series impedance of line decreases. Yeah, Ashish, what happened? Series impedance of the line will be decreased because natural series element is inductive in nature. By adding that capacitor, overall series impedance will decrease. What happens to shunt admittance? Almost no change. Almost there is no change in the shunt element. There is no change in the shunt element. What happens to ZC? Decreasing because Z is decreasing now. So ZC also decreases. SIL increases. SIL increases. V square by ZC. V square by ZC. ZC decreasing means SIL value increases. What happens to P maximum? What happens to P maximum value? P maximum. There is a good increment, right? There is a good increment in the P maximum because series reactance of line is decreasing. So P maximum value greatly increases. P maximum value greatly increases. P maximum value greatly increases. Okay, right. Next thing. This is about series capacitor placement. Next, third one we are calling now. Third one, shunt reactor placement. You write this one, shunt inductor, or you can write this as shunt reactor placement. Shunt inductor, or you can say it as shunt reactor placement. Series Z, what will happen? Series impedance, almost no change. Because it is a shunt element, right? Shunt element means series element will be almost same. What will happen to shunt admittance? Shunt admittance. Tell me please, shunt admittance decreases. Why? In the sense, natural shunt element is capacitive in nature. After adding shunt reactor, obviously overall admittance of the circuit will decrease. Overall admittance is decreasing and ZC value increases. ZC value increases. If ZC is increasing, SIL value decreases. SIL value decreases. What happens to P maximum? What happens to the value of P maximum? A small decrement in the P maximum will be expected because of decrement in the voltage. A small decrement in the P maximum occurs due to voltage decrement. Due to voltage decrement, I can say there is a small decrement in the value of P maximum. Right. So that's the third one. And fourth element, it is series reactor. Fourth element, it is series reactor placement in the system. Series reactor placement in the system. Yeah. Tell me please, series reactor. Series Z increases because natural element is inductive in nature and we are adding series reactor means overall impedance of circuit will increase. Overall impedance of circuit will increase. Right? And shunt, no change, almost no change in the shunt value. What about ZC? Increases. SIL decreases. SIL value decreases. And what about the P maximum? See, overall series reactance value will increase. Overall series reactance is increasing because of the series reactor addition. So P maximum value reduces. P maximum value reduces. These are the changes expected due to series reactor placement. So I think all of you getting it. All of you getting this one. Yeah. So what is the application of shunt capacitor bank in the system? Application, practical application, you tell me please. Practical application of shunt capacitor bank. Power factor correction. It's a power factor correction device. You're right. Device. Series capacitor. Tell me please, series capacitor. What's the practical application of series capacitor? Stability improvement device. Stability improvement device. Stability improvement device. Series capacitor. What about shunt reactor? Shunt reactor. Ferranti effect controller. Ferranti effect controller. Ferranti effect controller. What about series reactor? Series reactor, it will be used as smoothing reactor. It will be used as smoothing reactor. I'll write in the next slide better. Let me highlight that series reactor practical application. Series reactor. Series reactor, it will be used as smoothing reactor. Smoothing reactor to avoid the harmonics in current flow, to smooth out the current waveform, right? Particularly in power electronic circuits and HVDC. Power electronic circuits and HVDC will be using that as a smoothing reactor. Any other application of series reactor? Any other applications? To limit the fault current. It's a fault current limiting device. Fault current limiting limiter. Fault current limiter. Like that, we'll be using the series reactor. Clear? Yeah, practically, we will be using combinations of these elements only according to the place, according to the location, which system, what's the level of the system, what is the requirement. These things will decide. Combinations, not only one device. Not only one device, they will go with a combination of devices. Practically. Yeah. Good. So this is the end of the static devices, what we have. Next, we should move with the dynamic devices for compensation. That is synchronous motor application. Synchronous motor application. Yeah. So based on application and economic, yeah, correct, Vishnu. Based on application as well as economy, we are going to decide. Yeah. Listen. So next we are moving with dynamic devices for compensation. So first I will be taking up synchronous motor power equations. Synchronous motor power equations. Then we will see how it can act as a capacitor or reactor. Okay? Yeah. So I can say in the next slide, synchronous motor. Synchronous motor power equations. Power equations. Synchronous motor power equations. Listen to this. Synchronous motor power equations. Very simple to write. Very simple to write. Just like our two-bus system. So this is the synchronous motor connected. Synchronous motor connected to that particular bus bar. That I will keep as an equivalent circuit similar to generator. Similar to generator. So it will be represented with its internal impedance. And we have an voltage source here. Internal impedance and voltage source. And this is a bus bar at which we have a voltage mod V at an angle 0 degree, let us say. Mod V at an angle 0 degree. Okay. And this voltage, so-called the internal EMF. So it is mod E at an angle minus delta. This is the direction of the motor current. That's the direction of the motor current. Is V bar, you call it is IM bar. And impedance of this motor is JXS. JXS. Assume that this machine is a lossless machine. It's a lossless machine. Lossless motor, you can say lossless motor. Okay, now already we have given the heading now, power equations we want to know. Power equations we want to know. Power equations. Yeah, look here, look here. So real and reactive powers absorbed by the synchronous motor we want to write. Real and reactive powers absorbed by the synchronous motor we want to write. So I will be showing that here. This is PSM real power absorption plus J times of QSM, so called the reactive power absorption. Power equations, PSM and QSM. Yeah, you please tell me real power absorbed by the synchronous motor. Real power absorbed by the synchronous motor, PSM. That you can write as, listen please. Mod V into mod E, mod V into mod E by XS into sine of angular difference. Na? That sine of angular difference will come sine of 0 minus of minus delta. It will be sine delta. Mod V into mod E by XS into sine delta. That is a real power. Real power absorbed by the motor. Reactive power absorbed by the motor. Reactive power absorbed by the motor. So you can call it is QSM absorption here. QSM absorption. What's the formula? What is the formula for the QSM absorption? You see, first we should write mod V by XS. Two-bus system. It's just like a two-bus system. Two-bus system. Mod V by XS. First we should take this one. Direction from V to E. V to E. So I should write mod V minus mod E. V to E. Mod V minus mod E. Who is a reference? V is a reference. So E we should replace with E cos delta. E we should replace with E cos delta. E cos delta. All of you getting it? Please tell me. Just from the two-bus system expressions, we have written that real and reactive powers. Real and reactive powers. Okay. Now, this is a QSM absorption. Okay. What is QSM supply? What is QSM supply? Supply will be negative of this. Na? QSM supply will be negative of this one. Let me write that also. So let's say QSM supply here. QSM supply. It will be negative of QSM absorption. So this will come mod V by XS first term. And then here you get mod E cos delta minus mod V. Mod E cos delta minus mod V. Like this. Mod E cos delta minus 1. This is a QSM supply. QSM supply. Okay. Approximate equation only, neglecting losses. By neglecting losses, we are writing it. Losses. Okay. See, actually, listen, all of you. Listen. Actually, we will be designing the motor to meet the power demand, right? Mechanical demand. To meet the mechanical power demand, we are constructing and designing the motor. But right now, we want to use it as a reactive power compensator. Right now, we want to use it as a reactive power compensator. Let us operate the machine under no load. Let us operate the machine under no load and we will see what will happen if you are operating under no load. Right. So if you write at no load condition, what is the real power absorbed by the motor? You can write. What will be the real power absorbed by the motor? It will be 0, na? Real power absorbed by the motor will be 0. Right. So if it is 0, I can write mod V into mod E by XS into sine delta equal to 0. Mod V into mod E by XS into sine delta equals to 0. From this, you can write sine delta is 0 because these voltages and reactance, this value will not become 0. So sine delta will be 0. Then what is delta? You can say 0 degrees. Delta will be equal to 0 degree. That 0 degree you substitute in the QSM supply. That will give you The expression for reactive power supplied by the motor during no load operation. During no load operation. Yeah. All of you getting it? So can I move to the next slide? Take up the QSM supply at delta equals 0 degree. Yeah. So I'm taking up in the next slide QSM supply. QSM supply at delta equals to 0 degrees. Delta equals to 0 degrees will be mod V by XS into cos 0 is 1. So it will come to be mod E minus mod V. Mod E minus mod V. That's a QSM supply. QSM supply. Yeah. Under no load. Under no load. See, one thing what you have to observe here is this equation is not going away. Still, this equation is having an existence, right? Even though you say real power is 0, but still there is an existence for the reactive power. Means this machine is capable of supplying reactive power or absorbing reactive power, even though it is operating under no load. Even though it is operating under no load. Okay. So when this QSM supply will become positive means whenever this internal EMF is greater than the terminal voltage. When this is negative means when it will absorb means whenever the internal EMF is less compared to terminal voltage. Who is going to decide this internal EMF value? Excitation provided for the rotor field winding. Excitation provided for the rotor field winding. For example, if it's a overexcitation means E is more than V. At the time it is positive, means this machine is equivalent to capacitor bank. And during underexcitation stage, it will be an equivalent to reactor bank. So the first element I am going to take up here as synchronous condenser. Synchronous condenser, or you can say synchronous capacitor. Synchronous condenser, or you can call it a synchronous condenser. Sorry, capacitor. So basically, it's a no load operating synchronous motor with overexcitation. So it's an overexcited synchronous motor operating at no load condition. Operating at no load condition. It's an overexcited synchronous motor operating at no load condition. What do you mean by that overexcitation? What do you mean by that overexcitation? Overexcitation in the sense field current is high in number. Field current is high in number. Current will not become zero, Shraddha. Current will not become zero. Machine is operating under no load. That does not mean that current equals to zero. Na? Field current is high. Flux in the air gap is high. Induced EMF in the machine is high. Such that this E is greater than V. Okay. Then only it will act as a capacitor. Such that this mod E value was greater than mod V. Okay. Now you write QSM supply at delta equals to 0 degree is positive. QSM supply at delta So I'll write next slide better. QSM supply at delta equals to 0 degree is positive. Supply delta equals to 0 degree is positive. That implies you can write synchronous condenser injects the reactive power into the bus bar. Injects Q into the bus bar. Q into the connected bus bar. Okay. Bus bar. So it is acting similar to shunt capacitor bank. Acts in similar to shunt capacitor bank. Similar to shunt capacitor bank. Okay. Acts in similar to shunt capacitor bank. What's the practical application of shunt capacitor bank we said just now? power factor correction device. So this also acts as power factor correction device. Also acts as power factor correction device. What is that reactive power to be supplied to improve the power factor from cos phi1 to cos phi2 lagging? So amount of reactive power to be supplied is, to improve the power factor, amount of the reactive power supplied P1 into tan phi1 minus tan phi2. P1 into tan phi1 minus tan phi2. Okay. Q synchronous condenser is equal to P1 into tan phi1 minus tan phi2. For example, if the synchronous condenser, what we are talking now, if that is also taking real power, because it is a mechanical device, no, definitely it will take some real power, even though you say it is under no load. Even though you say it is under no load. In that situation, Q synchronous condenser, you should write as synchronous condenser, you should write as P1 tan phi1 minus P2 tan phi2. You should take it as P1 tan phi1 minus P2 tan phi2. P1 tan phi1 minus P2 tan phi2. Like this, we have to write Q synchronous condenser. Okay, next, let's take up the next element, that is synchronous reactor. Synchronous reactor I will take up. Yeah. So next device we have synchronous reactor. Sales. So it's an under-excited synchronous motor operating under no load. It's an under-excited synchronous motor under no load. Under no load operation. No load condition. It's an under-excited synchronous motor under no load condition. What do you mean by under excitation? Field current is less. Under excitation means field current is less, you can say. And obviously flux will be less. And induced EMF in the machine is also less. Induced EMF in the machine is also less, such that this induced EMF will be less compared to terminal voltage. Such that the induced EMF will be less compared to terminal voltage. Right. In this case, if you take up the QSM supply at delta equals to 0, QSM supply at delta equals to 0, it will be a negative number, na? Because you get E minus V here. E minus V, E is less than V, so it is a negative number. So a negative number in the sense, this synchronous reactor is going to absorb the reactive power from the bus bar. Synchronous reactor absorbs Q from the bus bar or from the system. From the bus bar or from the system. Similar to shunt reactor bank. Similar to shunt reactor bank. Similar to shunt reactor bank. Okay, next what I can say is, what's the practical application of shunt reactor? Practical application of shunt reactor bank, that is Ferrand effect controller. Right. So I can say it's a practical Ferrand effect controller. It can also be used as Ferrand effect controller. Ferrand effect controller. Yeah. Ferrand effect controller. But you see, these two devices, what we said, one is the synchronous condenser, other one is the synchronous reactor. These two, we will be using in olden days. For the application of power factor correction and Ferrand effect control, we will be using these devices in olden days. But at present, in the present trend, we are going with shunt capacitor banks and shunt reactor banks only. Shunt capacitor banks and shunt reactors, so-called static devices we are using. What are the disadvantages of using these dynamic devices for compensation? What are the disadvantages of using dynamic devices, so-called synchronous motor for compensation, I will write, right? So disadvantages are using synchronous motor for compensation. Disadvantages of using synchronous motor for compensation. Yeah. Tell me, anybody? Anybody, please tell me what are the disadvantages you can find? Please tell me. One thing, see, even though you say machine is operating under no load condition, but still the machine will consume a finite amount of real power because of the mechanical losses. So first disadvantage is no load power loss is non-zero. That's one disadvantage. Non-zero. Second disadvantage of the motor, synchronous motor, second disadvantage. Anybody? See, actually, maintenance is okay. You tell me about other things, other technical things you tell me. Technically. Yeah, listen now. See, we are using synchronous motor. It is not a self-starting motor, right? It's not a self-starting motor. So for that starting, we have to use some auxiliary motor. So no. So starting torque equals to 0. So it's not a self-starting motor. Not a self-starting motor. This motor is not a self-starting motor. Number three. Next disadvantage. Next disadvantage I am saying of the synchronous motor. Next disadvantage. Yeah, look here. See, we need a separate DC source for excitation, which is not required in case of capacitor bank and reactor bank. Just connecting capacitor bank to the bus bar is sufficient. But here, just connecting motor is not sufficient. We should give excitation for the field winding. So separate DC source is required for excitation. Separate DC source required for excitation. Required for the excitation. This is one thing. Separate DC source is required for the excitation. Next one. See, as and when we are adding the synchronous motor, you are introducing one more synchronous machine into the system that may be reducing the overall system stability. So it is going to show an effect on the system stability. Okay. So it shows effect on system stability. Effect on the system stability. Next disadvantage, I think already I discussed this in fault analysis. I discussed this disadvantage in fault analysis. Just go through it. For example, we have a generator connected to some load, something like this. Connected to some load. Okay. Now we are adding this synchronous motor as a condenser, let us say. Synchronous motor we are adding as a condenser. Now, if you take a fault on this line, short circuit fault on this line, this generator is supplying some fault current. This synchronous condenser also supplies some fault current. Na? Generator is supplying some fault current. Synchronous condenser also supplies some fault current. Yes or no? So, addition of the synchronous motor generally raises the fault level in the system. Right. So, fault level in the system will be increased. Fault level in the system increases. Fault level in the system increases. So these are various disadvantages we are getting. These are various disadvantages we are getting of using synchronous motor in the compensation. But there may be some advantages also. There may be some advantages also of using this synchronous motor. What are those advantages? That we should discuss now. Okay. Yeah. So let's see the next heading. Next heading. Advantages of using the synchronous motor. Advantages of using the synchronous motor for compensation. Yeah. Both capacitor inductor operation is possible. That's good. Same device, what you have purchased can be used as a capacitor as well as inductor. That's one advantage you can say. Same apparatus can act as inductor and capacitor. Same apparatus can act as inductor as well as capacitor. Inductor and capacitor. Okay, this is one thing. Next, second one you see. Yeah. So I will come back within 1 minute. I will come back within 1 minute. Please listen here. So next advantage I am saying, just look here with respect to capacitor. With respect to capacitor. For example, we have a capacitor bank, something like this here. Capacitor bank. This voltage is mod V. Voltage is mod V. Reactance is XC. Reactance is XC. Yeah. Please tell me, what is the amount of reactive power injected by the capacitor? What is the amount of reactive power injected by the capacitor? Formula. Mod V square by XC, na? Mod V square by XC. So this is some network we have. Network corrected. And we have mod V square by XC is the amount of reactive power injected. Similarly, this is a bus bar for which we have connected the synchronous condenser. And this is some network we have. Network with a terminal voltage of mod V. Terminal voltage of mod V. Now tell me, what is the expression for the reactive power injected by this one? What is the expression for the reactive power injected by the synchronous condenser? That is, we have derived mod V by XS into mod E minus mod V, na? Mod E minus mod V. This was the expression. Yeah, please listen. Please listen. Look here, please. Look here. Now you see the problem what I am saying you. See, actually, we are keeping that capacitor bank to maintain a good voltage at that bus. We are keeping that capacitor bank to maintain a good voltage at that bus. Okay. But you see, something happened in the network, some disturbance or something. Something happened in the network, causing for fall in the bus voltage. Causing for fall in the bus voltage. Listen, please. Because of the fall in the bus voltage, definitely this V square will decrease, na? Whenever this V square is decreasing, Q shunt capacitor also decreasing. See, actually, if this capacitor bank, if it is injecting more reactive power, it will maintain a good voltage at the bus. If the voltage is falling down, it is unable to supply a good amount of reactive power, and it is supplying less reactive power rather than the previous. Compared to previous number, it is supplying less reactive power. Then again, this voltage might have a chance of further fall. This voltage may further fall down. Because of that further fall, this Q shunt capacitor may decrease further. That may cause for decrement in the voltage continuously. And at some time, there is a possibility, I am saying, there is a possibility of voltage collapse. Voltage collapse. All of you understanding this one? All of you understanding this one? We are connecting a fixed capacitor bank. And you see, whenever terminal voltage falls down because of some disturbance, reactive power injected by capacitor bank also decreasing. Because of that, the terminal voltage further falls down. Again, reactive power injection further decreases. Voltage may further decrease. It may cause for voltage collapse in the system. But you see in the other case, synchronous condenser, if terminal voltage is falling down, terminal voltage falls down. Observe here. This is falling down. And you see, if this V is decreasing, E minus V will increase, na? E minus V will increase. So V is decreasing, E minus V is increasing. But still, you are having a capability of maintaining QSC in your view, in your control, by controlling this excitation EMF. All of you getting it? So that's the main advantage of using the synchronous condenser in place of the capacitor bank. So we have a control over the reactive power injection. And the possibility of getting voltage collapse. By using synchronous condenser will be less compared to shunt capacitor bank. Okay? Yeah. So I can say there is a good control over the Q injected by synchronous condenser, right? Such that voltage collapse problems can be avoided. voltage collapse problems can be avoided. Okay. Voltage collapse problems can be avoided. But we have many disadvantages of synchronous condenser. We have many disadvantages of synchronous condenser compared to it. But it is one of the very great advantage. One of the very great advantage. Now, listen. Now, I have to extract this advantage. I have to get this advantage. Remove all the disadvantages. Try to avoid all the disadvantages. How to do it? How to do it means, listen. For example, I am taking one equipment here named as voltage source converter, VSC. Voltage source converter. Voltage source converter. It's just like an inverter or rectifier. Doesn't matter. It may be an inverter or it may be a rectifier. One side of this voltage source converter, I am connecting one DC storage capacitor, or is a battery, whatever. Okay, DC storage capacitor, or you can say it's a battery. You can call it as battery. Other side, definitely you get an AC supply. Other side, you will be getting an AC supply. Okay, that AC supply, we have to connect to the power system network, or maybe line. This is a system, or you can say line. So that connection, to have a proper connection, I am using one transformer here. Okay, so that this system voltage is something like mod Vs at an angle 0 degree. And this converter output AC voltage is something like VC at an angle 0 degree. There is no real power exchange. That's why I'm saying both are at the same angle. Assuming that this is completely lossless equipment. Lossless equipment means there is no real power exchange. And this is having a reactance of XT, a transformer reactance I am showing as XT, transformer reactance XT. And the amount of reactive power injected here is something like QS. We are assuming some name. there, QS. This whole equipment what we have constructed with voltage source converter, DC storage capacitor, transformer. The amount of reactive power injected into the system is QS. What's the formula for QS now? What is the formula for the QS? Anybody? QS formula. Same as two-bus system, na? Mod Vs by XT. Into mod Vc minus mod Vs. That's it. Mod Vc minus mod Vs, cosine of angle cos 0, 1. Cos 0, that is 1. This is an equation for the reactive power injected by this equipment into the system. Listen all of you please. Is it looking similar to the synchronous motor equation? Yes or no? Which is in our control? VC is in our control. VS is system voltage, terminal voltage. Is it looking like synchronous motor equation? Yes, it's looking like synchronous motor equation only, but static. There is no rotating body. But it is static. It's not a rotating body. This we are going to name as static synchronous compensator. Static synchronous compensator, shortly called as STATCOM. It will be called as STATCOM. So it's a perfect replacement for no load operating synchronous motor. It's a perfect replacement for no load operating synchronous motor. It's a perfect replacement for the no load operating synchronous motor. Okay, it's having good efficiency and we can avoid the problems whatever you said earlier, right? But there is one issue. We have to keep this battery. Okay, yeah. So next we'll discuss one small problem, and then we will move to the next apparatus, next dynamic device, you can say. So what is that voltage source? It's a rectifier. Rectifier. It's a what we call harmonics introduction will be there definitely. It's just like a three-phase rectifier or three-phase inverter. It's an inverter. Let's take this problem quickly. Let's take up this. See this one. Very simple question it is. Very simple question. Here. A small industrial plant. In a small industrial plant, there exists 3 induction motors. Each operates at 0.8 lagging power factor and draws 1000 kilowatt individually. 1000 kilowatt individually. Okay. One among the induction motors is replaced with synchronous motor, which draws same real power, but operates at 0.707 leading power factor. The overall power factor of the plant is how much? Overall power factor of the plant is how much? That's the question. Okay. Let's say in the next slide. Solution. The case 1. This is an industrial plant. We have 3 induction motors here like this. Each induction motor will draw 1000 kilowatt. Each induction motor will draw 1000 kilowatt. Power factor is 0.8 lag. Is it so? 0.8 or 0.6? 0.8. 0.8 lag each one. 0.8 lag. Now, in the second case, what we are saying is this third induction motor, I am replacing with synchronous. Third induction motor, I am going to replace with synchronous. Synchronous. Yeah. So this is that replacement I am making. Synchronous. Right? Next, listen. This synchronous motor taking 1000 kilowatt only. 1000 kilowatt, but power factor is 0.707 leading. But the power factor is 0.707 leading. See, we have to calculate the overall power factor of system, right? Means plant, overall power factor of plant. Very simple. Whenever it is asked to find out the overall power factor, simply what you do? Find out the total real power consumption, total reactive power, take up real power by root of real power square plus reactive power square. That way. Okay. So listen. What is the total real power? Means this machine is drawing real power P1, it is drawing P2, it is drawing P3, P1, P2, P3, all the 3 are equal to 1000 kilowatt. So PT will come to be 3000 kilowatts. 3000 kilowatts. Okay. Yeah. So let's write. So total real power PT, it will be P1 plus P2 plus P3. It will be 3000 kilowatts. What about QT? Look here. First machine, induction motor, lagging power factor, takes the reactive power. Second machine, induction motor, lagging power factor, takes the reactive power. Third machine, synchronous motor, it will be supplying the reactive power, injecting the reactive power. So I can say this QT is equal to Q1 plus Q2 minus Q3 by power balance equation. Q1 plus Q2 absorption, Q3 is supply. So QT equals to Q1 plus Q2 minus Q3. Q1 plus Q2 minus Q3. What is Q1? Where Q1 is equal to, what you can write? P1 into tan phi 1. P1 into tan phi 1. That's a Q1. What's P1? 1000. Okay. Tan phi 1 means tan of cos inverse 0.8. Cos inverse 0.8. Tan of cos inverse 0.8. How much is that? Tell me please, what is this number? 1000 into tan of cos inverse 0.8. 750. Is it so? 750 kVAR. 750 kVAR. That's a Q1. Next, Q2. Q2. Observe Q2, which is P2 tan phi 2, na? P2 tan phi 2. So it will also come same, I think, 1000 into tan of cos inverse 0.8. So it will be 750 kVAR. 750 kVAR. Q3. What is Q3? It is P3 tan phi 3. P3 tan phi 3. P3 is 1000. Tan. What is phi 3? Cos inverse 0.07. Sorry, 0.707. This will come 1000 kVAR. This will come 1000 kVAR. Getting all of you? 1000. 1000. Now you can go for QT 750 plus 750 minus 1000. 750 plus 750 minus 1000. So I can write now QT is equal to 750 plus 750 minus 1000. So it will come like 500 kVAR. 500 kVAR. Okay, 500 kVAR. Now you find the overall power factor of system. Plant power factor, it is PT by root of PT square plus QT square. So PT number 3000 by root of 3000 square plus QT means 500 square. 3000 by root of 3000 square plus 500 square. How much is this number? Anybody please tell me what is this power factor? 0.986 lagging. Is it lagging or leading? Lagging only because overall plant is absorbing reactive power of 500. Overall plant is absorbing the reactive power of 500. So it will be lagging only. So 0.986 means option D is correct. Correct answer will be D. Correct answer from the options will be D. D. Okay. Next thing. Can you please tell me what is power factor in the first case? What is a power factor in the first case? Anybody? What is PT here? 3000. 3000. What is QT? See, it will be drawing 750. It will be drawing 750. It will be also drawing 750. So 3 into 750, that will be 2250 kVAR. 2250 kVAR. So with the help of this PT and QT, if you find out the power factor, it will come like 0.8 lag again. It will coming like 0.8 lag. It will come to be 0.8 lag. See, listen now, listen. See, in the first case, with 3 induction motors, we are getting power factor 0.8. Second case, by replacing one induction motor with synchronous with leading, we are getting a power factor of 0.986 lagging. Are you doing power factor improvement? Are you doing power factor improvement? Yes or no? Yes or no? Are you doing power factor improvement? Yes. We are doing the power factor improvement here. Okay. Now, whatever the synchronous motor you kept here, can we call it as synchronous condenser? Can we call this synchronous motor as a synchronous condenser? Yes or no? Yes or no? No. It's not a synchronous condenser, right? What is definition of synchronous condenser? What is definition of synchronous condenser? It's an overexcited synchronous motor operating at no load condition. No load condition. But right now, the machine what we are using here is experiencing some mechanical load, right? The synchronous motor what we are using now experiencing some mechanical load. So it won't be called as synchronous condenser, and it's going to be called as synchronous phase modifier. Okay. So this is going to be called as synchronous phase modifier. Synchronous phase modifier, or you can say phase advancer. Synchronous phase modifier, else you can call it as synchronous phase advancer. Phase advancer. Yeah. What's the definition of this one? What's the definition of this one? It's a synchronous motor overexcited. Definitely overexcited. Overexcited synchronous motor having some mechanical load on the shaft. Having some mechanical load on the shaft. Okay. So I can say the last equipment here, synchronous phase modifier, you can say phase advancer. So it is an overexcited synchronous motor with mechanical load on the shaft. Mechanical load on shaft. Some mechanical load on the shaft. Okay. So for example, if this is a phase modifier, if I show PM phase modifier connected to some bus bar, it will be taking some real power to meet the mechanical power demand. It will be taking some real power to meet the mechanical power demand. But it is injecting some reactive power because of its overexcitation. Injecting some reactive power because of its overexcitation. Okay. So phase modifier absorbs real power. Absorbs real power, but delivers reactive power. Delivers the reactive power. Absorbs the real power and delivers the reactive power. Let's write equations for these things. PPM and QPM equations. Similar to synchronous motor equations. PPM. Same equations of synchronous motor I am writing. Mod V, mod E by XS into sine delta. Mod V, mod E by XS into sine delta. What is QPM? It is absorption here and this is supply. What is QPM formula? Check this. Mod V by XS into mod E cos delta minus mod V. I think all of you comfortable with this? Synchronous motor only. Just today only we have discussed about it. Mod E cos delta minus mod V, where this delta is not equals to 0 because of existence of load on the system. Because of the existence of load on the system. E cos delta minus mod. Yeah. Next. See, when this QSM supply, so QPM supply will become positive. When this QPM supply will become positive. Whenever this E cos delta greater than V, E cos delta greater than V, then it is positive. So, QPM supply will be positive for a condition of E into cos delta greater than terminal voltage. E into cos delta greater than terminal voltage. Okay. So I am asking one very simple question to you. Very simple question. For the same amount of reactive power injection. Which machine requires more excitation? Is it condenser or phase modifier? For same amount of reactive power injection, which machine requires more excitation? Is it condenser or phase modifier? Definitely phase modifier. Because you see in condenser, we have to dominate the terminal voltage only by using E. But here E into cos delta should dominate the terminal voltage. Cos delta less than 1, so E value required will be greater to dominate the terminal voltage. So excitation required for phase modifier will be higher than synchronous condenser for same amount of same amount of reactive power injection. The same amount of the reactive power injection. Same amount of the reactive power injection. So this is end of this chapter. This is the end of this chapter. So I'm not going to take up the doubt session now. I'm not going to take up the doubt session now. But I will be available in mobile. I will be available in mobile for call. That's 96184-61918. Today from 10:30 to 1 p.m. I will be available with my mobile from 10:30 to 1. You can call me if you have any doubts. You can call me if you have any doubts. Okay. Call for doubts. 10:30 to 1. So please kindly excuse me. Okay. So yeah, you please put a request to me, Aparna. Please put a request to me, Aparna, in Telegram. Okay. Yeah. So I'm closing the session. Thank you.